All right.
Is it videotaping you?
Yeah, did
No.
you just get the video?
It makes it
No.
live so hard when we listen to videos and like so much.
Okay, so we just gotta, this is like this stuff, this is such cool stuff because it just brings everything we've done together. It's a great way to kind of review as you extend what you're doing. Let's just look at a few other types of problems. I want to look at one, this is a pretty good one to look at, and then we want to look at some examples of rational functions, how we deal with rational functions. Okay, so go. What do we do here?
Differentiate.
Okay, we are going to differentiate. How about let's get a domain?
Yeah,
could
and
do
then
that,
let's
I
do
suppose.
symmetry as well.
Okay, are there any?
Yeah, while we're at it, let's
While we're at
just
it, let's just use
knock two ants
Okay.
out with one.
Okay, symmetry in this case, first of all, let's do domain.
Okay.
What's going to be the part of this function that's going to restrict the domain?
The log.
The log, yeah. Everything else is fine, right? It's only the log that's going to impact it. And so we're going to inherit the domain of a log function, right? Which is just positive numbers, right? All positive reals. So our domain is this. Right? Okay. So because of that, do we need to worry about symmetry?
No.
No, because symmetry would be with respect to the origin or the y-axis, which would only be relevant if we had negative numbers in our domain, which we don't, right? So
Yeah.
don't have to worry about symmetry. Okay, so let's differentiate. All right, got a product rule, right?
Yeah, so negative 2x squared
Times.
times 1 over x.
Okay, so negative 2x.
I forgot the squared.
Right, but then we're going to multiply by 1 over x, right?
Yeah.
Yeah,
Oh,
so
so it's negative
yeah.
2x.
See what I'm saying?
Yeah.
Okay.
Yeah.
Okay, plus
No,
or minus.
Minus 4x. L
Log x?
plus 38x.
Okay, so we could simplify and get 36x minus 4x log x, right?
Yes.
Okay, so we could rewrite then f prime of x. We could factor that easily. What's the only thing we can do?
Let's take out a negative 4x.
Take out a
Plus
4x, okay? Or negative 4x. We'll just take out a 4x. 4x times 9 minus log x, okay? So then let's go ahead while we've got the first derivative just sitting there. Is it undefined any place in this domain? What's the only place it could be undefined?
Negatives.
Yeah, but we already know that our domain is already restricted because it was a log function, right? So no, we're fine, aren't we? I mean, the derivative is defined every place on its domain. So no place where it's undefined, no critical numbers there. I'll make a note of that. Right, so we're good. No critical numbers there. Where is it equal to 0?
Where?
Yeah, okay.
Where x is 0.
Log x, natural log x equals 9, right?
And with 0.
But is 0 in our domain? No, so we don't need to worry about 0, right? Because although the derivative is 0, the value of the derivative is 0 at 0, that's not even in the domain of the function or the derivative for that matter, because you can't take a log of 0, right? Okay, so that one's we don't have to worry about. We only get one critical number. If we solve that, what does that mean x is? If I exponentiate both sides, base e exponentiate, what do I get? X equals, yeah. That's a big number. It's crazy. Big number, right? Okay, so we get one critical number. It's some great big value that's going to be out there like pushing 10,000-ish, like, 8,000 something maybe, something like that, right? So it's a big number. What about our second derivative? Because they're asking about, okay, they're not asking about inflection points, but I will, right? So let's find second derivative. Where would we want to differentiate to get the second derivative?
What?
Equation.
Wait, what? Wait, what'd you say?
We want to calculate f double prime.
Yeah.
Where would we leave off from our first derivative? Do we?
Oh,
There?
no.
No,
Ew,
it'd probably
gross.
easier to go
So
there.
much better.
Yeah,
Oh, yeah.
way better, right there. Right. Okay, so we get 36, good, minus
Minus
4.
4,
Yeah.
right? 4x times 1 over x, so that's just 4.
4.
yeah.
Minus,
4x ln x. No, minus 4 ln x.
there you go, right? So that's the same thing as 32 minus 4 log x, which is the same thing, factor out of 4, right?
Yep.
4 times 8 minus log x, right?
Yes.
Okay, so then in fact, I'm gonna go ahead and do this. Let's rewrite that over here so we have it in a convenient space. Factored form. So then we get a 0 of our second derivative at, log x equals 8, right?
Yeah.
So x equals e to the 8th. Okay. Make sense? Okay. Big numbers. All right, so now really it's just a matter of making our table, right? So let's do that. Oh, you know what? I had a table sitting down there. How about that? There. All right, so our domain, we said, extended to the right of 0. We had one critical number way the heck out there at e to the 9th.
Yeah.
So 0 of the first derivative, and e to the 8th is a 0 of the second derivative, right?
Yeah.
Okay. All right, so what do we do?
Let's
Let's
evaluate
take,
e to the 9 at
let's like
in the second
find where,
derivative.
no, wait.
So sign of second derivative where?
Wait, what?
What?
Well, okay, say what you were saying again.
The second derivative?
Yeah, right,
Yeah.
we want to do the second derivative test at e to the 9th. Knowing the value of the second derivative there contributes to knowing if that's an inflection point, but it also tells us what kind of extremum that is, right?
Yeah, for
Exactly.
sure.
Okay, so then let's do that. If we evaluate, where's our first derivative? Right there, right? So f prime of e to the, f double prime, sorry, of e to the 9th
I feel like it would.
is what? F double prime of e to the 9th would be 4 times 8 minus natural log of e to the 9th. What's the natural log of e to the 9th? 9. Yeah. So I'm getting negative, right?
Negative.
Oh, wow.
What?
Right?
This is
Right.
tricky.
Okay, so we got horizontal tangent. What's going on?
Sad face.
It's a sad face. So that's a maximum. Okay, smooth maximum. We want to know what's going on here. So what do we need to do to determine if that's an inflection point?
We
You
need to
put a
we
point
need
on
to-
the other side.
Test point on the other side. Let's just pick. How about if we just pick E?
Oh, it's-
Yeah, that's what I was listening to, but that works.
So if we just pick E, the value of the second derivative at E.
It's just.
Okay, we said this was
It's positive.
negative. Right.
That's a
Okay.
happy face.
F prime of E is going to be what? That's going to give us 4 times 8 minus 1, right?
Yeah.
Positive. So this is
Inflection point.
an inflection point. There you go. And if we want to know, just so we have an idea how to make our graph, let's get some y values. So we need our inflection point and our maximum. So what's the value of our function at e to the 9th? At e to the 9th, we're going to get, oh boy, that's just going to be a big number. Somebody just plug that in.
Yeah.
You know what? We don't even care. It's just going to be some big number. Right. And then we're going to get the same thing there. We're going to get e to the 8th is some still big number. This is a very big number. This is just a big number.
Mr. Ward?
Yeah.
For the second derivative, 0,
Mhm.
could it be anything other than an inflection point?
Yeah, doesn't have to. It's only an inflection point if the second derivative is 0 and it's a transition in sign. Otherwise, it's not.
So what else would it be if it wasn't? a transition?
Well, okay, here's an example. Remember, we looked at one like this. We looked at this, right? We looked at x to the 4th. Right? Remember the derivative. So x to the 4th has a 0 first derivative and a 0 second derivative at x equals 0, right? But it's not a point of transition of concavity. And so what it ends up being is just a minimum instead. Okay, make sense? You could have one that's not a minimum, but it's also not an inflection point. Like what if I had something like this? Like what if I'm gonna try to graph this. So if I had a function that did this, if it went something like that maybe. This point right here could be a 0 of the second derivative, but it may not be an inflection point. It's just a point. Pans out to be nothing major. Okay. So if we graph this guy, then it's got to look like what? Well, in our limit, well, what's it look like? It would just look like this.
Actually, I have no
Just look like that.
idea. Okay, actually it's close.
Okay, make sense? Now those are really big. Look at the scale of that.
That's insane.
Right, those are big.
Whoa.
You know, like this thing is, it's like pushing, 6 point something times 10 to the 7th, right? 10 to the 7th is 10 million. So we're looking at 65 million-ish or something is going to be the height of this thing, right? That's the value of the function at the maximum. There it is right there, right? And look how big the x value is, right? That's e to the 9th. There is going to be an inflection point down here somewhere too. I guess it doesn't show you inflection points, but there's an inflection point kind of like, I don't know, like right in there somewhere. Okay. Here, let's find out where.
X equals E8.
Yeah, x equals e to the 8th, exactly. And then we'll just look for that intersection. There it is. There's the inflection point right there. Okay. Make sense? Okay. That's a pretty picture. We need to get a photo of that, don't we? A little snapshot.
It's really good.
That's so good. So good. She got her calculus class in the background. That was a good one. Oh. Okay, there it is for posterity, for your notes. All right, let's look at one of these. Okay. So rational functions. Now this time, asymptotes become more relevant, right? This is one where we could potentially have some horizontal asymptotes or slant asymptotes. In this case, horizontal asymptotes. So we used to do stuff like this, right? We had a rule. Remember this stuff? Guidelines for finding limits at plus or minus
not
infinity of
really.
rational functions, right?
I have no recollection of that.
I remember you telling
Remember
us
this,
like
right? If the degree of the numerator is less than the degree of the denominator, then the limit is 0 at the infinities, and so we get a horizontal asymptote at y equals 0, which is right on the x-axis. If the degrees of the polynomials are equal, then we get the ratio of the leading coefficients, right? And if the degree of the numerator is greater, then we don't get, we don't get a limit, right? We don't get a fixed limit. We could get a slant asymptote or an oblique asymptote if the degree of the numerator is how much bigger than the degree of the denominator? 1. Exactly 1. Yep. Okay, now this stuff gets a lot easier with L'Hopital's rule, doesn't it? If we just took this limit as x approaches plus or minus infinity, yeah, it's indeterminate now, but if I just differentiate this twice, don't I just end up getting 2 over 2, which is 1?
Huh?
Right?
Yeah.
Everybody
Right.
agree? So
Yeah.
my answer is 1.
Yeah.
Right? The limit is 1. So we get a horizontal asymptote at y equals 1. Right?
Okay.
Yeah, 'cause the ratio of the,
Wait, is y equals
it's
1
the
or is
ratio
x
of the
equals 1?
Right?
because
Oh,
if you use
right.
L'Hopital's rule, then it would just be 2x over 2x, which would mean
Okay.
it's 1.
Gotcha.
We can't choose find x squared, x squared, that's 1.
No, because you have 3.
But that doesn't matter. So you're speaking terms.
Yeah.
I would not have done it one step further.
Right?
Yeah.
Okay, good. So we got that. Do we get any vertical asymptotes?
Oh, square
That's a
root.
good question.
Yeah, negative the square root of 3. But that's not possible because it's squared.
That's right. It's so that we don't get any, right? There are no real zeros of the denominator, right?
Yeah.
It can't be
Okay.
negative.
Yeah, because it'd be imaginary. Okay. So we get no vertical asymptotes, but we do get a horizontal asymptote. Okay, so that tells us a lot, right? Now we just do calculus. What's our domain?
All
All reals, yeah, right? All reals because the denominator, again, can never be 0, right? So we're fine.
Yeah.
Okay, so then we just need to differentiate.
Yes, we do.
Okay, quotient rule, what do we get?
Low times 2x minus 2x or x squared times 2x
I agree.
over x squared plus 3 quantity squared.
There you go.
That was very smart of you.
Okay, so that's gonna give us, what is that gonna give us? 6x over quantity x squared plus 3 squared, right?
Yeah.
Oh,
Okay.
yeah.
Okay, let's calculate a second
There's
derivative.
one more. We can do
Quotient rule again.
it. Okay, this one's, okay, so the bottom. 11
Yeah.
times 6 minus 2 times the quantity x squared plus 3 times 2x times 6x
Okay,
over the quantity x squared plus 3 to the 4.
aha, okay.
We're on fire.
Okay, so let's see what we can do. We could simplify a bunch of stuff there, right? We could make
Yes.
that a minus 24x squared.
Bro, how do you do that?
Right?
Yeah, I'm not gonna argue with it.
Yeah, that's
Agreed.
good to me.
Okay, over our denominator.
That's really long.
Why don't we factor out x squared plus
Okay, and what could we do?
Factor out.
Factor out what on the top?
x squared plus 3.
Okay, and what
Oh, and
else?
a 6.
And a 6, there you go.
Gosh dang.
Leaving behind,
X squared plus
X squared
3
plus 3.
minus 4x squared.
there you go, okay? Divided by that. But we could do a little cancellation here,
Yeah.
right?
That would come through.
Good. And we could combine some like terms there, and we got this
We
thing
cleaned
pretty
that
well
up.
cleaned up, don't we? So then we end up with 6 times,
X.
let's make that a negative 6. Factor out a
Yeah.
negative, so that becomes a 4x squared. Oh, never mind, that
3.
becomes
Becomes a 3.
3x squared, yeah. Minus 3, aha.
So we can multiply them.
So we could take a 3 out, couldn't we? Right?
We sure could.
Okay.
Dang guys, we're gonna do
Okay, so let's get some critical numbers. First derivative. Any undefined anywhere?
Whoa, okay.
Wait,
Okay.
wait.
There's our first derivative, right?
Yeah.
Undefined anywhere?
Nope.
Nope, good. 0 at 0, okay?
Whoa. Oh. Wait. Oh,
Right?
the first. Wait. Oh, yeah. Sorry.
Okay. Because that's the 0 is the 0 of our numerator, right? Okay, how about down here? Second derivative. Y prime is 0 where?
At 1.
Or
Square root of.
Square root of 19.
Oh, square root of 1 is 1.
Square root of 19.
Square root.
Negative 1.
plus or minus 1, right? Because when x squared equals 1, so x would equal
Yeah.
plus or minus square root of 1.
That's right,
Okay,
that's right.
there you go, okay? All
We
right,
need a lot of stuff, but-
so let's see, do I have no, we need a table. Let me grab a table for us.
The what, Grace? Your little phone.
Where's my calc table? Calc table.
Her legs, her ankles, her back.
Right,
My legs are so.
I saw you. right
there we
there.
go, look at that. There's my calc table.
I saw you, yeah.
And I had my mom. My car.
Oh, I didn't see that.
Okay, yeah, well, just look at my backpack. I was like,
I've never honked my horn on purpose, but I have accidentally.
oh, well, we did last night.
Okay, you guys tell me now, I'm gonna start passing the baton to
Okay.
you. You guys tell me what to write on the table.
Let's
Oh, okay.
fill it out.
So we've got infinity and negative infinity
There
at the
you go.
end.
Okay.
Well, negative infinity and
In
infinity.
parentheses, not brackets.
Yeah, yep. And then we have the positive and negative 1, yeah?
We have 0 and then.
And then we have 0, yeah. We have 0 too. right in the middle.
And
Okay, so
Smack
what
dab.
goes with zero?
Zero.
Zero.
Is
Zero
zero
Where?
for the first derivative.
Oh, okay.
Yeah, why?
And then for the,
The other ones
And
are the
one.
double derivatives.
they're down.
They have zeros right there.
Okay,
Yeah.
good. Now
Okay.
what?
Now we're
Can
gonna
we plug
find
zero into
the
the second
second
derivative?
derivative.
Okay, so the sign of the second derivative at zero
Yeah, I wanna know.
is
0 minus 1.
Positive.
positive. Yeah, I'm gonna get negative times negative over positive, right? So I get positive,
Okay.
which means what?
It's
Touch the
happy.
happy face.
Okay, good.
Okay. Test point.
Okay,
Yes, we do.
Test points now.
all right, test points, where?
Negative 2 and 2.
Yeah. So we can see if it's in a question.
There we go. Okay, so let's see, let's go up here and evaluate our second derivative
Okay.
Alright. So it's gonna
of negative
be
two.
negative over
So, yep, negative over.
positive.
Positive,
So
so
it's
negative.
What?
And at positive,
It's negative as well.
same thing, right?
Yep.
So I'll just do this.
Wild. So they're both inflection points.
Yes.
What?
Okay, are you starting to suspect some symmetry here?
I'm
It
starting to
might be.
suspect a lot. It does look pretty symmetrical to me. That
Okay.
Okay,
seems-
well, we could check symmetry.
Let's.
You guys can tell me
Seems
what's
pretty
the symmetry of the numerator,
Even.
symmetry of the denominator.
Even.
So what's the overall symmetry?
Even.
Even, yep. Okay, so we do get even symmetry. Good. So we're gonna get folding symmetry about the
About
Origin.
zero.
axis. Good.
Yeah.
Okay, so what else? One other thing we could do,
Let's plug.
limits.
We could.
Oh, wait.
What's
Ew,
the limit
no,
of the
we
function
can't
as
do
x
that.
approaches negative infinity?
Garbage.
Infinity. 1.
Yeah, it was 1, wasn't it?
Oh.
Right? The
Oh.
limit as x approached plus or minus
Oh, yeah, 'cause
infinity
the
was
ratio.
1.
So it's 1 on both sides.
Yeah.
So what's that telling us? We'll just make a note right here. Horizontal asymptote on the left, horizontal asymptote on the right.
Okay.
Isn't that cool? Look how much stuff we got out of that table. That's everything, right?
We can still keep going.
Don't stop.
What else could we do? I think we're good.
We're good? We
I
can drop
feel
I
it?
think
good
we're
about
good. I mean, we could get some values. What if we just plugged in
No.
some points? What's the value of the function at 0?
Wait,
The first.
zero.
The first
Yeah,
one.
the
No, the
first one.
function.
Okay, yeah.
0, right?
Zero.
Okay.
0.
So we get the point 0,
0, 0.
0. How about at 1?
1/4.
Okay, and at negative 1?
1/4.
There you go. So now that's a lot, right? We could take that stuff and make a pretty good, in fact, let's do that.
See a pretty graph.
Isn't this kind of fun? It's just like doing a puzzle.
It's fun when it's not on my homework.
Yeah, it's fun when we do it in
Then I
class.
can't figure it out.
Not when I'm by myself. No making stuff.
Well, that's the next step. That's actually really fun when you start to get these things and you're like, man, that's really rewarding feeling.
I mean, you can do it by yourself.
Yeah.
But it's so lonely.
Yeah, it takes a whole army to get this done.
The math gods are always there with you. Don't worry about it.
I think they've abandoned me at this
Yeah, I
point.
think they like to leave.
I've fallen asleep too many times.
It's gross.
I hope it's not raining during practice.
No,
No, we don't, 'cause we have to
Because
run
I
our
look
building.
like a wet rat when I'm
And then your mascara runs and like, it's stupid and you're
Well,
cold and wet.
We want rain. We want rain. Tigger actually slept on the corner and it was raining. But it's funny, but it's also like not. It's like scary.
Well, because I know she's okay, I think.
like at all.
It's scary though, cause that's like, get her.
Okay, so let's fill this
I don't
in,
wanna
right?
slip on the track, that would be dangerous.
I did that once.
I bet you.
So what do we got here? We've got a point at 0, 0.
0, 0.
The origin, that's point on the graph.
Okay, so
And that's
0,
gonna be
0.
symmetrical on both sides of
Oops.
that. Good thought.
We know we've got reflective symmetry about that. We've got a point at 1, 1/4.
Yep,
So right there.
yep. And we got it on the other side too.
On the other side too.
Yep.
And we've got a minimum and an inflection point, and it goes to 1, right? So we have a horizontal asymptote.
What?
Right there. Yep.
So we know what this has to look like then, right? It
It's
has
gotta
to
be
go.
smiling up and then.
It just goes.
Oh, no, not
No,
that.
I was gonna say, I was like,
Not
what
that.
are we doing
Because
here?
that would require another maximum, wouldn't it?
Yeah.
It's just going,
Yep, just
right?
beautiful,
Wow.
beautiful.
Isn't that, man,
She
that
really said-
is really beautiful. Feel very artistic. Okay, good. All right. Okay, let's do another one. Okay, you guys talk me through this one now.
Okay.
Okay, so we
Pick
gotta
the
find
range.
the domain.
Domain, good.
It's the
What's our domain?
It's, yeah,
Yeah.
Okay, good, yeah.
Real talk, right there.
X cannot equal again what?
Positive or negative 1.
Okay, what's going on there?
there's like a little, there's a thing.
There's a
Vertical
asymptote.
asymptote.
Vertical asymptotes because those are unique zeros of the
Of the
denominator. There you go.
She's like,
Okay. The limit of 3x over x squared plus minus 1 as x approaches plus or minus infinity is what?
Oh wait,
it's
when
zero. It's zero.
0.
Because it's a bigger on the bottom, right?
Yep.
Yeah.
Yep.
It's infinitely bigger on the bottom.
That makes so much sense. Wait, yeah, I get that actually. Yay.
Okay, good. And we could use L'Hopital's rule if we want to, but we don't need to, right?
No, we don't need the hospital.
Okay, good. We got lots already. Symmetry.
It's
It is
negative odd.
Yeah.
Odd, I mean.
Odd, yep.
That's the-
I know what you mean. You're using your analogy. Odd over even is
Is
odd.
odd.
Yep. Okay, good. So we'll make a note of that.
You're just using your analogy. We appreciate the effort.
I knew what was.
Okay, and derivatives. And we're pretty good here.
Derivatives. Okay.
We're on our way.
Loading high, so it's gonna be x squared minus 1 times 3 minus 2
Just trying to
X
keep up, Aubrey. You
times
have to go slower.
3x over x squared minus 1 squared.
Times what? 3x times?
2x.
Oh, you couldn't keep up.
I couldn't.
Lame.
squared minus 1 squared.
Quantity squared.
Quantity squared.
I'm getting a carpal tunnel up here trying to keep up. So then on top, that gives me 3x squared minus 3 minus 6x squared, right?
Yep.
So then
So-
if you
So
combine that,
negative
so negative
3x
3x.
squared minus 3. We can take out a 3, so it's just gonna be
Take out negative 3.
negative 3
Okay.
x squared plus 1 over x squared minus 1 squared.
Okay,
Woo!
right?
Yeah.
That looks alright.
Make sense? Okay. First derivative, undefined anywhere?
At
At
1.
1. Positive and negative 1.
Okay, but that doesn't matter. How come?
Because
that's
it's
a
not in
limit.
the.
Because it's a limit.
How come?
It's
It's
not
not
our
our
domain.
Not in our domain, so
Yeah.
it's irrelevant. There you go.
Yeah.
Okay, is it 0 anywhere?
No.
No,
Not.
that's nowhere 0, right? Top has no
Nowhere.
zeros.
Yeah.
So no critical numbers. Are there any extrema on this function?
No.
No?
Whoa.
No
Do we
extrema.
even keep doing it then?
Okay.
So are we done?
Well, yeah, then we could have inflection points.
You're
So we gotta go again.
Okay. Okay.
Okay, so we
X
wanna pick
squared
up
minus
probably
1 quantity
right
squared.
there, don't we? Right.
Yeah.
Yeah.
So let me write the denominator. Okay, so go.
Okay. X squared minus 1 quantity squared times negative 6x minus negative 3x squared minus 3
Whoa, wait.
times 2 to the x squared minus 1 times 2x over x squared minus 1 quantity to the fourth.
All right.
Wow, that's a lot.
Okay, it's a lot, yeah. Okay, so we could clean that up a little bit, how about?
Yeah.
Yeah, let's
An
make
extra
it up
minus
a lot.
Proceed to factors we bring out.
Okay, so here we got a minus 6x, x squared minus 1, quantity squared. Over here, let's see, we've got we could go ahead and maybe distribute that, right? So we get, and we could factor, how'd we get, that's right, isn't it? What did we do there? 3x. I'm sure it is, but what did
Yeah.
we do?
It was,
We just give up.
so negative 3x times 2x is negative 6x squared. And then it's 3x squared, so we combine that to get negative 3x squared.
Oh, there, that right there,
Yeah.
yeah. Okay, there we go, yeah. Okay, so if we distribute that negative, we're just gonna get plus, let's factor out a 3. Right, factor a 3 out of that.
Sure.
So we're gonna get 12x times
Oh,
x squared plus 1 times x squared minus 1. Does that look right?
Yeah,
Anybody buy that?
I think so.
Okay. So in the bottom is the same. We could, now what could we factor out of the top?
We could factor out 6x
Okay.
and an x squared minus 1.
Okay, 6x, yeah, 6x and an x squared minus 1. I like it. Leaving behind,
a negative x squared minus 1.
okay, and then over here we'll put the positive term first. That would be
And then that one would be, so it'd
2.
be 2 times the x squared plus 1.
Oh, I'm running out of space. I gotta go the row down.
Exactly.
Yeah. So we got 6x times x squared minus 1 times, what's left behind? From this term, we got 2
2 times
X squared plus 1 minus
x squared
Minus 1, right?
Yeah. Yep.
all over.
All over x squared minus 1, and then we can do it to the third because we can cancel out the
Good.
top.
Okay, so we cancel one of those. Everybody with me?
yeah.
Yeah.
Okay.
It's looking good.
And then this is looking a little better. So then we get, on the top, we're going to get 6x. Now, what's all this going to be? We're going to get 2x squared minus x squared is x squared plus 2 plus 1 plus 3.
Yeah.
Okay. Over x squared minus 1 cubed. Okay. So any place where our second derivative is 0.
No. Besides 0?
0.
0.
Zero.
Yeah.
To find the derivative of equal
At the top, because I think it's undefined at the bottom, 0. Unless the top also equals 0.
Okay. And wasn't the top?
Then you
Oh,
have
we had
to
no critical numbers of the numerator.
No.
All right. So now we can make our table.
It's not.
I do not like when you have to go to this.
Okay. So what did we find here? We found our domain was
All reals except positive and negative.
positive, negative, 1. Aha. Okay, so then
It's gonna be
those,
tricky.
positive 1.
I just don't know what.
Okay, look what we do with the table on this one then. Positive
Yeah.
1 and negative 1. It's where our function is undefined. And so we just write vertical asymptote up here and make a dashed line.
Oh.
And that's gonna carve our
Okay,
function up
okay.
into those 3 different regions, right?
Yeah.
Okay, we had a 0 of the second derivative at 0.
So we'll need
And otherwise our function extended
Yeah.
out to
To
infinity.
the-
Okay, we had limits was 0, right?
yeah.
So we had horizontal asymptote. Okay, there's a lot of stuff.
Yeah.
Look at all those asymptotes we've got now. That sets up our
That's
graph.
wild.
Oh,
One
man.
more deal.
Just, we're having fun. Okay, we'll finish this one up
Yeah,
tomorrow.
we'll finish
Okay,
it tomorrow.
after we talk about the sonnets.
Okay.
Or